Hey everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Vedam with Atlanta Functional Programming. I'm hoping all of you are having a wonderful Halloween holiday, given the circumstances. Today we're going to be going into a deep dive of a library that I've been wanting to go into after some discussion last week. We've covered this in the past, but we never really dug deep into how it implements a couple of things, and that is the Screamer library for non-deterministic programming and backtracking. I provided in the links for folks who have missed that episode or want to review it prior to coming back to this episode in the YouTube description. So for folks who are watching this live, who want to go back and maybe watch that first prior to coming back and seeing how we're dealing with certain things, you can certainly do so by clicking on that link, going, watching that discussion, and then coming back to today's episode to kind of see where we're, how it kind of works at a much more deeper level. Before we get started, a couple of announcements for folks in the Atlanta area and virtually. We're going to be having a discussion and having a presentation by Judd Taylor on Hi, a Lisp that compiles to Python AST code and integrates well with the Python ecosystem on November 11th at 7 p.m. Eastern Standard Time. The links to actually go and watch and view that, the YouTube links particularly, are available at meetup.com. If you're signed up to the meetup list, you can certainly go to Atlanta Functional Programming to that event, and you can find the information to actually go in and view that particular meetup on November 11th. Additionally, we're still looking for speakers for new talks and topics. So folks who are interested in giving a topic in at Atlanta Functional Programming, please feel free to ping me or Dagmar on the Functional Programming Slack channel. We're usually hanging out in the Lisp chat room there. I'm also available on the Lisp Discord server if you want to DM me. I'm Bugram on the Lisp Discord server. Additionally, I'm also available for folks in the Atlanta area specifically who are members of Tech 404. I'm on the Tech 404 Slack server too, as well as Bugram. So please, contact me. Let me know that you have a topic and talk, and we can get that scheduled. To begin our discussion today, I need to first obviously create a new project. So I'm just going to go ahead and do that. As usual, I'm going to be using CL Project to generate the new project. Let me just raise the font size here. Make sure that everything is good. Yeah, good. All right. So let's create our project in Roswell Local Projects, AFP Screamer demo. And obviously, for folks who are not familiar with CL Project, you need to specify the depends on to actually go and grab what you need. In this case, we're going to be obviously grabbing two libraries, one Alexandria, and then, of course, Screamer. Let's go ahead and load this guy. AFP Screamer demo. And while that's doing that, I'm going to go in here and load our basic library. Also, so to begin our kind of discussion into Screamer, we need to kind of get into. I need to kind of give you a little bit of a brief review of the Screamer library, and again, folks who want to see more of a usage, please go to the YouTube link that I provided to actually get more information. But to review what Screamer is a library, like I said, that actually was designed for um, non-deterministic programming. What does that mean? So for folks who are not familiar with non-deterministic programming is kind of a way of allowing you to provide a graph of multiple options within the state of a program and allow the program to determine based on particular avenues, whether it's in a failure state or a success state. The way Screamer does this is through the use of what it calls choice points. A choice point operator being something that allows you to give Screamer a way of saying, oh, this is a success path, please continue this path, versus um, this is a failure path, you can no longer further traverse the graph from this point on. To best illustrate this, I'm probably going to just show you kind of an example that was brought up in our past episode as a review. Of course, in order for us to do this, we're going to have to actually go into the Screamer package, and Screamer actually has a very nice package that allows us to experiment with Screamer as is, and that is the Screamer user package. So a good example that is actually inside the documentation that we kind of covered was grabbing, let's say all the odd numbers inside of a given list. So you could specify here, probably easier for me to put this in the demo here. Yeah. So I'm going to go and show you how I'm going to technically use this. There's also another way later on in our discussion today when we start really diving into the Screamer library on how to define Screamer packages. But for the time being, I'm just going to use the exported symbol notation to actually grab stuff from the Screamer library. So in this case, what we're doing is let's say that we're going to try and grab, the all the odd numbers. Of course, given the fact that we're in our script, we're going to have to print them out. Here, I'm just going to grab, let's say, let's make this a little bit more interesting. Let's go ahead and make a list of 10 integers. Actually, that will not work because of the fact that this is a Screamer list. So to grab all the odd values and traverse through this, what we do is we first create a choice point here using the iter operator. The iter operator means that you're telling Screamer that each value in the list of values that I'm providing is a potential value that can go down this tree. So it will allow Screamer to explore each one of these values to see which one could be a success state or a failure state. So here we specify, let's say, 5 values, and what we could do is we can check to see if we hit an odd number, then we just return it. Otherwise, what we do is we call Screamer fail. Okay. Let me see. Fail. Okay. And Screamer fail isn't just a simple. It isn't just any simple function. What it's ultimately doing is it's creating a failure state in what we could define as maybe a potential state machine. And when we run this, what we ultimately get is the list of odd numbers. Now, this may not look like anything spectacular. You could certainly use this in a lot of different ways. But this simple example illustrates that what Screamer does ultimately is it gives you the option of defining multiple paths inside of the Screamer package, and what Screamer does is it uses its propagation model to take each value in this list and go through its model to determine whether or not it's a success or a failure. And it does this iteratively, in a sense. Now, you can certainly use Screamer to actually create, you know, many different types of graphs. But, you know, again, as a quick review, what this ultimately allows you to be able to do is create different types of constraint propagation models inside Common Lisp, and it's tightly integrated into the Common Lisp ecosystem. And it can be similarly used to implement models very analogous to how you would use maybe, say, Prolog and define backtracking constraint propagation in that language. Of course, for folks who are aware of how there are, you know, Prolog packages, you know, out there for Common Lisp, why would you then want to use something like Screamer? Screamer provides a couple of additional very quick library, convenient functions, so to speak, that gives you the ability to collect, grab one of, grab different types of uh, unique values within a set or within a constraint propagation model. Additionally, it has a way of doing allowing you to define a model such that you can undo effects. This is something that we didn't really cover in detail last time, but we did, you know, mention briefly that you can, you know, undo certain types of effects inside the library if you use this. I'm just going to quickly just show two additional examples, one with generators, one with side effects, before we start doing a deep dive on how this kind of library works. But very quickly, to illustrate this from the documentation, has a good example of this. You can define generators using the same sort of syntax. First, we need to obviously example of generators. Just make sure of something. Okay, cool. We could create something called an int between, and we provide, you know, a lower bound and then an upper bound, minimum, maximum, and we check to see. Oops. We check to see if min is greater than max, and if it is, that means we failed. Otherwise, what we would do is we go either min or, and we make a recursive call to an int between, and we increment min and max, so that this is a recursive definition of a function that will generate potential values between min and max. And obviously we can define this here, yeah, because of the fact that I did not use Screamer here like I should have. Okay, so now what we do is let's say that we want to grab, you know, one value between, let's say, 5 and 15. Okay, let me just do this, go to my REPL, and a boolean is a non-deterministic function. It must be defined. Did I mess that up? I didn't believe I did. Interesting. Maybe one value required. Something else. Let me see if this requires more things here. Okay. So the reason why it was failing earlier is because of the fact that internally what this is doing, one value is it's using another exported symbol, another screamer specific symbol called a boolean to check to see if the predicate actually matches or not. And since we didn't actually export all the screamer symbols into the package, it's complaining. I think the way to handle this here is using screamer defun, because there is a way of defining it that way. Let me see. Yeah, that's the reason why. Okay. So Screamer, just like series last week, and our is a compiler that takes ultimately a set of functions that you defined inside the Screamer model, and then it compiles them into this backtracking based model that can then leverage everything that's in Screamer for going between different paths, seeing if they hit failure states, and being able to backtrack to a previously successful state and so forth. And that is what we're going to be doing a deep dive in today. Let's see if there's questions. Since I'm not looking at this right now. Cool. All right. So, and if we go and do this, we can see that it's going to always hit 5, because 5 is always going to successfully be between 5 and 15. If we, of course, say all values here instead of 5, we'll get everything between 5 and 15. And it'll just do an increment generation of this. You can also, like I said before, do things like undoing of side effects. An example of this is, and let me be a bit more specific as to what the documentation says about this. If you have generalized expanders, that is expressions that use set f or set q, okay, and this includes calls to user-defined setf functions. You can undo those with Screamer because Screamer internally has a way of being able to determine that okay, we hit a failure state. Let's go ahead and backtrack, which means let's undo the effects of all those setf expressions and then go back to the previously set state. So think of it almost like a rollback of in a database sense. However, for functions that are destructive operations, and I'll give you a few of those, things like replace car, RPL, ACA, replica, or sort, where internally it actually sorts the underlying data structure. Screamer has no way of knowing, because all that's in place within the actual algorithm, to be able to undo itself without keeping an extra copy of that information, so it chooses not to undo those operations, assuming you know what you're doing. An example of this would probably be, let's say that we want to grab all the values between a certain range whereby we are incrementing the the counter as the number of values that we've returned. Okay, so an example of this would be, let's say here, and I'll put this in the replica in the REPL. Let me clear this so that we can actually have some room. Let's go ahead and start our things with some counter variable. Let's say n, and we create, a associative array where numbers is the list of all values between let's do this. Let's do the example that's in the way. That's between xb and into between 0 and 5. And what we'll do is we're going to increment n, and x is going to be returned. All right. And what we'll do is we're also going to keep track of the value n. All right. So what happens here is as the value is getting incremented, the underlying n is actually, as the model is getting incremented, the underlying n is going to be incremented globally, because it's internally to the model. Into the let form, n is actually just localized there, right? So the inc f, since it's internally a set f to an inc the 1 plus operator, it's going to go ahead and modify the n variable and then return it. Now you could certainly mitigate this and say, oh, you know what? I want to be able to actually only localize the side effects internally and scope it, but I don't want it to be chained globally. You could certainly do that. And the way you do that in Screamer is through the use of the local and global macros, where you're essentially putting in hints into your code to determine whether something is a global modification or a local modification. So to illustrate this in this example, let's go ahead and add an additional counter variable m. And what we'll do is we will go ahead and use local to actually determine that we're going to be incrementing the n variable. So n is now a local modification, but m is going to have a global modification. Okay. And then we're going to go and return m and n. You'll see the difference here. M is getting globally modified, where we essentially said to the model, hey, you know what? I'm okay with this global modification. I don't want you to go and change anything. But as soon as Screamer leaves its model, n, because it was tagged as being a local change and it's used as a scoped variable, it doesn't shadow the original value of n, and n is set to be kept at 0 in this example. Now, of course, we've also talked about a little bit last time on the constraint propagation aspects of Screamer. And there was a sufficient amount of examples brought up there. I'm not going to repeat some of that here, but I will say that for folks who want a brief introduction to it, the simplest example of how Screamer does constraint propagation is it does forward. It has both backtracking as well as forward constraint propagation using logic variables, much like the way you would use it if you did forward inferencing inside uh, um, a language like a logic programming language like Prolog. Now, the examples are pretty straightforward in the documentation. I'm not going to really illustrate some of them here, but we will dive into how some of this stuff works into when we're discussing, how the underlying compiler actually gets all set up. But that's a quick overview of the Screamer library. Before I start diving in anything, is there anything in particular people want to ask regarding the usage of the Screamer library? I know I went pretty quickly there. It was a very brief introduction compared to the 2.5 hour discussion we had on the topic originally, but that's only because I want to have some time to actually go and dig into um, the internals of the library. So I'm just going to wait just 1 minute here, setting up with other things, just to see if there are questions, and then I'll continue. Sure. Okay. Looks like there aren't any questions, so I will continue. All right. So Screamer and the non-deterministic Lisp variant has been around for quite some time, actually. It is a It was originally created in 1991 for folks who are interested in the actual original papers that are related to it. I encourage you to, and I'm just going to briefly show this for folks. I'm going to add this to the GitHub, the YouTube description, but the original set of papers related to Screamer, and it's all part of the Screamer GitHub by Nicodemus. It's on GitHub. If you go to the repository for Screamer, you will see the AAAI 93 and a couple of other papers related to it. We're going to go into some of the more underlying details of the code, but I wanted to at least mention that because there is some sound theory related to the Screamer library that might be of use for folks, especially folks who are looking at designing maybe building off a Screamer and designing their own constraint propagation systems. But it is essentially a set of macros to define your model of logic variables and how things work in the library itself. And we will kind of like dig into that a little bit today. To begin with, I think it's important to understand that, excuse me, that Screamer at its heart is a very tightly integrated high-level compiler to Common Lisp. And what I mean by that is like Series, Screamer has its own set of macros, and this includes reader macros, some shadowing imports. It overrides defun, as you saw earlier, and some other built-in common Lisp symbols. So how do you go in and create then a package that works with Screamer, but doesn't complain about name resolutions? Well, Screamer internally already creates some of this, and that is through the use of macros itself. It has its own macro called define Screamer package that allows you to essentially define packages normally like any other package, but it handles a lot of the shadowing imports for you. 1 second. What the heck? Oh, sorry. For some reason, did that. Okay. So instead of defining package like this, you can, actually go ahead and do. Oh, sorry. Heck? There we go. You can go ahead and do Screamer, define Screamer package, name the package AFP Screamer demo, and internally, provide the options that you want to, define. Now, if there's, and since it's much like, it's essentially a wrapper around def package, a lot of the def package arguments will work. Although this is redundant, I'm just going to show this to you. You could do something like this and then define it, and you'll see that it's going to be complaining about this because right now I've defined a Screamer package within something that's already been done. So let me go ahead and make a new file here. Something here. I may have messed this up by doing that. When in doubt, go back to what it was originally. All right. Let me go ahead and create another file here. Test basic package.lisp. And here, let's do Screamer define package, basic package. Basic package. And if we define that, you'll see that it compiles and loads. Obviously, now we can also use basic package here, and it's going to go ahead and work. Let me go and change this way. If we look in our REPL and we set our package, you'll see basic package being there. And now the difference here is now using define Screamer package, you have essentially the Screamer not only defines the use of both Common Lisp and Screamer, but what it does internally is and you can see this in the with more details in the documentation. There's a bunch of there's a couple of things that it shadows, specifically defund, multiple value bind, yes or no questions. All that are actually shadowed. We can actually see this if we expand this macro. Give me a second here. Macro expand. This is essentially what it boils down to. Now, this might sound like, well, there's only 3 symbols here that it's shadowing. Why do I need to use this versus just doing a straight up common Lisp, def package. Well, they might be adding more in the future if you end up using this library. So having the shadowing imports there being controlled by the library will save you time in some subtle bugs that might occur when you're leveraging the Screamer package itself. So, like I said, Screamer is itself a compiler. Let's take a simple example of what might happen, and let's take the example that we were talking about before, which is the all values, and go through each of the individual pieces of a basic Screamer program to see how different parts of the system will actually get compiled by the underlying Screamer metacompiler to Common Lisp, just so that we can get an understanding on how this backtracking could be implemented. All right. To start with, we're going to go back to what we originally wrote, which was, but I'm just going to go ahead and, since I have a Screamer package here, go ahead and use all values without the package colon. Again, if you're using normal def package, you have to use Screamer colon for the exported symbols, but in this case, since we've defined it using Screamer and things are shadowed and we're using the entire Screamer package internally, like we had before, if we do this, you can see that Screamer is actually, all of its symbols are actually imported into the package like Common Lisp. We don't necessarily need to actually preclude all values with the Screamer colon. And so let's go back to what we had originally, which was a simple check to see if we had an odd number. Otherwise, we fail. All right. So this here internally, it's going to generate a significant amount of code. Okay. And what it's doing is I'm going to go through it piece by piece. When Screamer starts compiling something using either all values, none values, or for effects, okay. For effects is itself a macro that creates what's called they create a context, a non-deterministic context, which essentially is a generated prog-n with different logic related to the first choice point, the first direction that the tree needs to go down, and it will maintain the side effects that are within that for effects section before a failure or a success happens, and then it returns. And in for effects, my understanding is it actually keeps track of what needs to be undone. Okay, so if we look at this example of grabbing all of our values, this is actually showing us exactly what. One second, let me get this video. Yeah, there we go. It will actually show us what Screamer compiles, expands the macros to. In this case, we started with for effects. For effects will generate a choice point. Again, we talked about choice points. Choice points are essentially these points in the tree to determine potential paths to traverse down. And internally, it creates continuations dealing with particular paths that need to be executed. Okay, one in this case is a path dealing with actually checking to see if something is an odd number or not, and then the other one is dealing with the actual generation of the next value inside the either let's hit the the either form that we actually had originally. All right. Let me see if I could actually do a side by side so you guys can see the before and after as we're expanding this macro. Since I have this available here, let me just do this. Okay. And just bring this down. It's a short script, so it's going to be a little difficult to align it, but that's fine. Let's go ahead and expand this. So this is the initial expansion. We start with all values with an either form, and then some code related to what ultimately should we be doing if it's odd or not. We provided a predicate to determine how do we know we're in a success state or a failure state. When we expand it first, the initial expansion creates this, which is I'm going to take a for effects. I'm basically essentially creating this non-deterministic context. The context contains, all the paths that we were talking about. And what it does is it repeatedly backtracks itself until either the body fails or it returns. And then when for effects returns, like I said, all the side effects will get deleted that are in a local context. Okay, so in the case of 18 through 22 in this macro expansion, 23 in this macro expansion, since these are labeled as global, as for effects is running, it will actually not delete those. Those are actually going to be stayed. They're going to be continue to be modified. And ultimately, you could see right here in line 24, what is ultimately returned by all values is some sort of collection that is initially set to null before it actually gets modified later on. In the second expansion of this guy, this is we're gonna dig a little deeper into how for effects works. For effects actually creates two continuations, like I mentioned before, and what it does is it takes those two continuation fun calls them at the appropriate time. Let me see if I can actually do this like we had before. And again, not going too much into the weeds here, just because when you start talking about continuations, we have to kind of map through how the different continuation paths are being generated. But the main thing to know is we're generating these two deferred computations. One related to actually doing the check and returning the actual collected value, and the other determining what the next value in the collection is to go and run through the deterministic context. Both of which ultimately then modifies this global value 719 collection that is generated when the macro gets expanded. They both result in ultimately modifying that collection and then returning it. So what happens through all this, and this is where this main thing is happening, this here is ultimately what's doing the modification, the first continuation. The second continuation is mainly modifying the context to know what the next value is. Okay, I haven't dug deep into what Screamer magic is, to be quite honest, so I can't really tell you what this magic function does. If you bear with me, we can go and look at the code to go and figure that out. Let me see if I can pull up the code here. And here. Yeah, let's go ahead and do that. Let's see if this works. Yeah. Let me share this my screen here. Give me a second. Screen share. Okay. Pull this down. See if you're seeing that. Okay, perfect. So, all right. And let me share this with my friends. To begin with, what we were talking about before was, how does this screamer magic kind of come into play? But to really understand that, there's a couple of things that this library kind of does in order to get to that point. Because if you go and actually look at screamer magic, it's actually all the way down, very at the bottom. And but there's a lot of stuff related to the underlying environment that might be of use for folks who are interested in how some of this kind of works. So I'm just going to kind of go through just very quickly some of the underlying things in the some of the core principles of the underlying library that we're going through. All right. To begin with, there is, of course, the non-deterministic context part of this. What exactly is that entailing, right? Because that's something, of course, that kind of sets up the actual infrastructure for us to actually do our to do the propagation and the traversal. So that's actually right here at the top. Before you define anything, there's a couple of interesting functions that are determined here. You don't really need to go through this in detail, other than the fact that this is just making sure that when you define, say, functions, compiles, times, structs, and variables, and so forth, using def var, defun, def structs accordingly, these actually get hooked into the underlying non-deterministic context later on, which is what we then use instead. So def var compile time, def var and def struct compile time is what we ultimately use to define our actual non-deterministic context, which is deferred right here in line 90. and later on, what it uses that information to go and do that in combination with the actual trail to go and do backtracking. The trail is what's ultimately keeping track of the current form that you're executing, and it's using whatever it needs to do internally to actually go behind the scenes and undo some of the operations that may have occurred. This is how things like side effects can be reversed in a sense, because we're keeping track of like a history of what changes are actually happening within the local context that we can unwind when we're going back to and backtracking to a different path. Additionally, this notion of choice point is what's essentially marking inside of this this trail. Well, not the trail necessarily, the model itself, the point at which we can actually provide some ability to undo or redo certain operations based on what path we're actually going through. So I don't think I'm going to do a thorough code review today here, just because it's really pretty involved in terms of how it's actually taking these pieces. The one piece that I do want to actually bring up is given this infrastructure that's in place related to defining these functions and setting up all this plumbing to actually do backtracking, the one thing that most users of this library need to be aware of is how do you define functions using Screamer? How do you define the appropriate interactions with Screamer when you're dealing with side effects? And what additional like hints could you use? What additional conveniences could you use? Here, that I'm the reason I stopped here between line 149 and 156 is it's kind of giving you what exactly the context is, and the different types of contexts where you can that you get as part of the Screamer library. Function bodies with Screamer defun have a non-deterministic context for macro invocations, all value invocations, one value invocations, and so forth. We haven't actually tried, say, print values, ith value, possibly or necessarily. Those have been covered in their use in our last episode, and again, I defer you to go and look into that. But here, I'm mentioning them just merely because in terms of the actual context creation, they each get their own non-deterministic context. I'm reiterating that piece because different context means that there are going to be different states that you need to kind of keep track of, and especially when you start talking about local versus global modifications, as the library allows you to do. You need to know which context that you're in to determine whether or not something is going to be really localized or globally expanded and adjusted. There's a bunch of other things related to compile time expansion and so, that the library does. And this is particularly important for symbol resolution, making sure that function names are valid and all that kind of stuff. But that's all part of the pre-processing of the actual Screamer program before it actually gets executed. So a lot of this stuff is just, kind of compiler infrastructure that needs to be put in place in order for the Screamer compiler to take a high-level Screamer program that's written in its API and expand it to proper common Lisp. And it implements things like walking and some primitive tree shaking in order for you to leverage some of that. Are there questions about this? Let's go back to here. Okay. So let's go back to Emacs here. Let me just switch back. Okay. And let me go back here. All right. And let me go back to this main thing for constraint propagation. So to really, drive this home in how this is going to be, this this is leveraged in, say, a logic programming sense. I'm going to go ahead and grab uh, the example that's in the documentation for assertions for logic variables, and we're going to explore actually what exactly is it doing behind the scenes in in using these logic variables to actually build out the model and use the all values or print values for particular um, use cases. So the example that this is using is something that's pretty typical in uh, when you're trying to introduce logic programming to many folks, and it takes a simple, let's say, variable. Let's call this guy, you know, the answer. Okay, and it's a logic variable in that in 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 Screamer, or if you're thinking about it in the Prolog sense, this can be any value inside your fact base, all right, inside your knowledge base, all right. Here we're calling this guy the answer, has a name, because as you see here, make variable takes in a name, the answer. So if we go and look at this guy here, the answer, you'll see that it is a logic variable that is the answer. Let's go ahead and constrain this guy, saying that this answer is going to be only an integer. Okay, and to do this, we're using assert bang. Again, I have to reiterate the same thing when I was looking at this. Assert bang in the Screamer sense is not the same as the exclamation point in the Scheme sense. For folks who are coming from Scheme, who are looking at this and are thinking that this is an unmodifiable operation, that is not what its intent is. It is a simple notation to determine that this is being registered in the fact database, the Screamer knowledge base, so to speak, to what's it to insert new facts. This is what this assert is doing. All right, it's asserting facts about, particularly in this case, we are asserting a fact about the variable that we just created, the logic variable, and that in this case we're saying that, and this is integer PV. Okay, so when we use integer PV, we're saying that this guy, in the Screamer sense, this is an exported function in the Screamer, and we're saying that this guy is going to be an integer, right? Now, initially, you could see that if we go back to here, we saw that the answer is currently unconstrained, okay? There's no information about what type of variable this logic variable is holding. What type of values this logic variable is going to have, okay? By using this assert, we've effectively said now that this logic variable can only hold integers. So if we end up having, in our constraint model, a way where it gets assigned a string, we violated the logic variable and throw it up an error. All right. So let's go in and assert something about this value. All right. So constrained the logic variable integer. We just said that this is how we define logic variables. Now we're going to go ahead and assert. Well, we're going to say insert into our streamer package that. Well, actually, what I'm going to say is that we're going to further constrain this variable to be 2 less than what the answer is. Okay. And what this is doing is what we're defining is essentially constraints on the problem that we're trying to figure out. We're having essentially the engine, the underlying Screamer engine, to figure out the answer for us. All right. So we know that the variable is an integer. We're further asserting that, and we create these further constraints. We're saying that the equals v, which is actually a logic variable value equality operator that's defined in Screamer. We're saying that in this case, 40 has to be at least 2 less than what our answer is actually. Okay. So think of 40, right, the answer as being a value x, all right? So we've defined that it's an integer. It has to be 40 2 less, 2 less than, 2 more than 40. So if we actually go in and ask what the answer is, internally it has already pre-computed this value, all right? How did it do that? So whenever you define anything, it internally keeps track of in the model what the answer, what the value needs, okay? And when you define these further facts and further constrain it, it is just adding more information to this, to the underlying context that has been created as part of creating this this logic variable. So internally, the logic variable itself is actually what's it? The logic variable itself is an underlying context that keeps track of this this information as you're asserting about things about it. So internally, this has metadata about itself. Okay. So to illustrate this, you can actually see this. Although in the REPL we're actually saying we're actually getting the answer, if we actually do a type of on this value, you'll see that this is just a screamer variable, all right? And the internal value of this is just 42, okay? So how did that, how did it suddenly get the 42 directly? Well, they overridden print object and a couple of other things, and for using class to actually take screamer variables and be able to dump out their contents to the REPL pretty easily for convenience for working in the REPL. But if you're actually wondering about that value, you can simply inspect it, and you can see that this is actually a pretty, should I have done this? Go and inspect, not evaluate. Do this. Slide, inspect, definition. That's right. Slide, inspect. Okay. So a screamer variable keeps track of what its logic name is that we provided in the constructor. Additionally, it keeps track of what its domain is, anti-domain is, its value. There's a couple of convenience methods to determine, some of the primitive types. So if you go and call possibly integer or non-integer or so forth, it has all that information ahead of time, and it can go and compute some information about that. When you're creating this, each time you provide information about, screamer, about the logic variable here, the answer, internally, the logic variables, it actually has a set of observers, you could think of it that way, that are closures that are going to get executed in the order in which you provide some of the information. And it will then use that to actually go and determine an answer for it. If there are obviously multiple answers, that will make things a little bit interesting. I don't believe there is an example of this. There might be. Let's see. We can do that with, here we go. If you have multiple answers, then this is where backtracking's advantages become very, very useful. All right. We talked about this before in the past with an example using houses. I don't remember all those details right now, so I'm just going to go with a simpler one. We're going to create example of constraint problem with multiple answers. We're going to create two variables, okay, x and y. We're going to go ahead and assert these guys. Okay, we're going to assert them to be both integers. Again, for folks who are using do Emacs or even space max, if you see integer or integer p, what you want to use is integer pv when you're defining it in the screamer package. And we're going to define both these logic variables to be essentially integers. Again, we're going to provide the initial constraint that we want them to be. We want the sum of their stuff to be, say, 42. Okay. The that's y 42. Actually, I take that back. We're saying that the sum of these two and 42 is going to become 0. Okay. So we're essentially going to probably dump out, a bunch of negative numbers, or some combination of negative and positive numbers that satisfy that initial equation. All right. So now, if we want to get all the values between them, we have this non-deterministic context called all values that allows us to provide, two things here. One, of course, being an integer between let's say minus 50 and minus 30. And for folks who are just tuning in or wondering where an integer between or an integer below and all that came from, there's a bunch of convenience methods that are already available at your disposal that's part of the API that you can certainly use. So, so now we do an integer between 2 and 5 here. And we're going to first, assert that x is equal to one of these. Oops. That y is equal to this. And then we're just going to return both of these. Now you might be wondering why we're asserting both of those. That occurs, actually, you know what? I take that back. This is control x, control this. Let's see if I can do this. Control star. We need to actually compare these guys. That's what we need to be doing. And no. There we go. Okay. So what this is doing is it's first binding essentially with this equals v x to x and that y to y, and then we're going to return the two as soon as they satisfy this particular value. All right. So if we print this, you'll see what it's doing is again, it's taking the values that an integer between is providing, and it is essentially hold on one second, just realized this is not properly indented. What we did was we defined it in a top level constraint value, all right, constraint equation on two logical values. And we provided some further constraints on the number of integers that we're doing in the search space. And by running all values, we've effectively executed this search space on the model and see if we've satisfied this additional equation. All right. So this is essentially what Screamer is all about. You're declaring your top level search question, so to speak, and you're having Screamer figure out based on additional constraints that you're providing a set of answers and allow it to essentially prune the tree and then run through the search space. And again, the way it does this is if you macro expand just all values is through this simulation where it's taking two continuations, one creating the next value or next set of values that it needs to go and run through the model, and then it will run the actual model itself. This the question that I have, that I'm still trying to play around with to come up with a decent example is, would this hook up into using in other contexts? Like if we're trying to use different compilers. I can't say that for certain. It took me a while to try and understand how the constraint propagation model is actually working. But for folks who are watching this, if you really want a sum up sentence on what it's doing behind the scenes, it's essentially grabbing the environment, grabbing the constraints associated with the logical variables, creating a context that keeps track of this information, traverses through the possible state space that's defined by the constraints. So in this case, x's constraints is between -50 and -30. Y's constraints is between 2 and 5. It binds those by asserting this equality operator, and then it returns them in when they satisfy the actual constraint equation itself, which is in this case, verifying that the sum of those two plus 42 is going to be equal to 0. That's a huge mouthful, but it really at least illustrates some of the particular advantages of using this kind of design for programming. You could design a lot of different logical programs in this declarative way, and you'll be able to at least be able to debug the programs just by looking at their rules, and you're doing this forward propagation of rules. I don't know if it can do back propagation in the sense of the way Prolog does some stuff, but certainly if you have time, I'd encourage you guys to go in and explore and see if that kind of works. Is there anything else that I want to talk about? There is one thing that was here. Hold on, in this case, solution when the system is. Right. So, the real magic on how a lot of this works is through a function called solution, but I think we kind of ran out of time for today's thing, so I will let you guys take a look at that. Basically, I could try and explain this. But this is really just a pretty involved thing. It essentially determines, given a list of arguments and a ordering force function, it will go internally and make sure that the values, when bound, satisfy that ordering force function, so that you can actually further constrain the search space when you're actually binding these to the different logic variables. But again, I haven't had a chance to go and explore that particular piece of the library, and I encourage you guys to take a look at it. And if you have questions, comments, or any particular concerns or things that you want to bring up, post it in the YouTube comments. I will get back to it, and I will mention it in our next meeting. So that's it for me today. I hope you guys have a great Halloween, and I will see you guys next week. Thanks.